Section 2 of The National Geographic Magazine, Volume 9, November 1898. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2021. What is the Tide of the Open Atlantic? By Mark S. W. Jefferson. The writer has sought to collect the known facts of the tides of Atlantic North America and study them in relation to the geography. At the present date, the mathematical theory of the tides has reached a considerable degree of perfection. The theory of geographic influences can hardly be said to have been formulated. Analysis has succeeded in predicting the tides of tomorrow from those of yesterday, but no description of shore configuration and submerged topography will yet enable the mathematician to predict the time and height of the tide at an unknown port. Give him a series of observations at that place, and he will learn from the local constants and compute the future tides with accuracy. This is indeed the only end he has had in view, and it is of great practical importance. The results now accumulated are sufficiently accurate and numerous to deserve comparative study. Furthermore, much light is shed upon this study by the hints that analysts have dropped by the way, if a layman may venture to interpret them. But for Farrell's Treatise on Tides, the present paper could not have been written. Most readers would find the mathematical work veiled in mystery, and not all mathematicians condescend to draw aside the veil. Diurnal inequality, for instance, affects low water little or none, and high water much. A mathematician states that harmonic analysis shows it must be so, and we may get what enlightenment from it we can. In such a study one is immediately struck by the twofold aspect of the problem. 1. The tides of theory reside in the deep ocean. 2. The tides of observation belong to the margins of the land. Data given for tides in the open ocean refer merely to the shores of oceanic islands, and it should be borne in mind that tides on the ocean do not admit of measurement by any means as yet at our command, though it is not inconceivable that the gauge may be lowered to the ocean floor, which should record fluctuations of pressure by means of an electrical communication with the surface. All study of the tides must therefore proceed from the shores. Subdivision of area. The tidal stations for our area fall naturally into two groups as regards distribution in 1. The landlocked waters of the shore itself, and 2. The shallow waters bordering North America on the east. Brief notes on the tides of the first area, estuarine, have already been published in the September number of this magazine. Certain water bodies of form not unlike the estuaries there studied could not be included in that paper from the anomalous character of their tides. These are the Bay of Fundy, Vineyard Sound, Buzzards Bay, Narragansett Bay, and Long Island Sound. For these waters and the general tidal phenomena of the shallow offshore waters, we get light from the consideration of the tides in the open Atlantic, and we immediately see that the older view of the ocean tides is in conflict with the facts now widely observed. This was the view of the progressive wave and the co-tidal lines. Many difficulties are smoothed over by limiting this conception to the shallower shore waters and supposing the ocean basin to be the seat of a stationary wave with vibration period adjusted to the motion of the moon. Progressive and stationary waves. A pebble dropped into still water sends circling ripples in every direction from the point of plunge. The ripple is a little wave that travels off till overcome by frictional resistances or stopped by the shore. It is a progressive wave. To form it, a number of water particles in succession move up, forward, down, and back, as may be noted by floating sticks and straws. such a wave is produced at or off the mouths of estuaries and travels up them. The velocity is supposed to be that acquired by a body falling freely through 1/2 the depth of water. Footnote. To make this available in rivers, we need a formula for integrating the varying depth and recognition of the effect of width. Now that the Delaware has been gauged, such a study is possible. End footnote. If you lift one side of a basin or tub partly filled with water and quickly lower it again, the water within oscillates as a whole in a time dependent for any one vessel on the depth of water. The water on opposite sides rises and falls, up at one side when down on the other. Along a line across the center there is no vertical motion. It is a stationary wave with a central node. As with a pendulum, successive oscillations are in the same period, but the period may be changed by changing the depth of water. If the nodal axis lies north and south, as when the east end of the vessel has been lifted, the motion of the water particles is simultaneously to the west, then simultaneously to the east. A fall on the east corresponds to a rise on the west, the amount of rise and fall depending on distance from the node and, much more, on local configuration. Stationary waves may be studied in a tumbler of water, and the experiment should be tried. The earlier view. It is usual in tidal discussions to assume a general case of convenient conditions and come later to the real problem, the tides in the case of nature. The general case supposed was a sphere uniformly covered with water. The moon was considered to have the power of heaping up the waters at the points of the earth nearest to itself and farthest away. The deepening of the waters at these 2 points would be accompanied by a shallowing around a circle equatorial to these points as poles. Thus, the ocean would assume the shape of a prolate spheroid, with longer axes always pointed at the moon. The earth would always have its 2 high waters at its opposite points, with low waters in between. In the mean 6 hours 13 minutes, a half-lunar day, would intervene between high and low, and between low and high. This spheroidal shell would seem to revolve about the earth with the moon, alternately elevating and depressing the water surface of any place. The first assumption to reject for the actual world is the Earth's uniform envelope of ocean. The Atlantic is barred east and west by continents. The apices of a tidal spheroid cannot come to this water body in a daily swing about the Earth. When the moon is over the eastern border of the ocean, it might heap the waters there in a tide that would accompany it in its apparent westward path across the ocean, but at the American continent this action must for the moment cease. Each ocean would see the birth and death of a tidal wave at its eastern and western bounds. Below the southern continents, in latitude 60 degrees, is a ring of continuous ocean, with tides probably simultaneous 180 degrees apart. Footnote. South Georgia and Auckland Island, near this circle, are distant 9 hours 15 minutes of longitude. Their tides differ in time 9 hours 47 minutes. End footnote. This belt alone, then, conforms to ideal conditions. It is hard to say when the idea of deriving tides from this southern ocean arose. Lieutenant J. Cook, reporting tidal observations for the South Pacific, asserted in 1772, "I am fully convinced that the flood comes from the southward, or rather from the southeast." Laplace seems to have entertained a similar idea for the Atlantic, and assigned a day and a half as the time it took a wave to come from the main ocean. The earliest attempt to draw co-tidal lines was in 1807 by Dr. Thomas Young. It is a sketch of the British Islands, with coasts of France and Norway and progressive tidal lines. The lines were drawn straight, crossing the English Channel nearly at right angles to its axis, and in other places springing squarely off from the shores. In a supplement to the Encyclopaedia Britannica, written in 1823, Dr. Young suggested the tracing of co-tidal lines, indicating sources of data, declared the scheme impracticable, but collected and reduced the data for 150 stations, and described the general course of a tidal wave advancing up the Atlantic at least as far as Gibraltar. Dr. William Whewell took up the investigation in the 30s. From all the charts, sailing directions, and ocean pilots he could obtain, he computed co-tidal hours for points all over the world, being the time of high water on the day of new or full moon. From these data he traced the progression of the tide up the Atlantic to the coasts of Europe and America, deriving it from the belt of ocean to the south. He published his co-tidal chart in 1833. He was fully conscious of the very crude data given him at times by observers who fancied the tides always occurred at the same hour, and he closed his first essay with the warning that the results were only tentative. Figure 1 reproduces the Atlantic portion of this chart. Dr. Whewell was moved by this lack of good data to seek the cooperation of the Admiralty to have careful observations made simultaneously at least about the British shores. He not only accomplished this, but was enabled in 1835 to publish observations made according to his instructions at 666 stations in America and Europe, with 2 at the Cape of Good Hope, for every tide between the 8th and 28th of June of that year. The greater part of these were about the British Isles, and for this region he published a revision of his chart. For the American coast he contented himself with pointing out some errors in his first chart. The rest of the chart he abandoned until a wide range of good observations should be at hand. Difficulties of the earlier view. Now, defects in the general scheme of co-tidals are defects in the theory of a wave progressing up the Atlantic from the south. These defects Whewell found to be based on 1. The extraordinary manner in which the co-tidals contour about the lands, together with the difficulty of including the oceanic islands in the system, and 2. The great difference of epoch of the diurnal wave in Europe and America, together with the identical epoch in Spain and at the Cape of Good Hope, supposed to be separated by a long journey up the Atlantic. A comparison of Whewell's 2 maps of British co-tidals, figures 3 and 4, with Dr. Young's 1807 sketch, figure 2, shows the growing appreciation of the contouring tendencies of co-tidals. With the abundance of fairly good data at hand today, it is everywhere observed that co-tidal lines adjust themselves closely to the shoreline. With reasonable depth, it is quite usual for high water to appear far up a bay as early as at its mouth. High water reaches the head of Placentia Bay, Newfoundland, about a half hour before it reaches the headlands on either side of the mouth, as may be seen on the accompanying sketch, figure 5, where 3 stations are shown, at the bay head and at either side of the entrance. The upper figures at each place indicate the interval between high water at St. John's and local high water. The lower figure indicates the tidal range in feet. From the line of 100 fathoms it is evident that the impulse is transmitted to the various stations with a delay dependent on distance from the deeper water, yet there is no tide of the progressive estuarine type. This failure is complete in the 3 characteristics of time, range, and front steepening, since the interval from high water to low water is 6 hours 13 minutes at all 3 stations, implying equal front and back slopes in the tide wave. Buzzards Bay has tides that reach almost all its shores at the same time, as if originating at some point central to the bay. Dr. Bache, in 1864, noted the essential feature that its tides are nearly synchronous at the head and all about the bay. To illustrate this, Figure 6, besides showing the tidal interval for each station from no man's land, shows also the 30 meters co-tidal. There is certainly no progression up the bay here, nor is there any perceptible increase in tide ranges. The duration of rise is greater than that of fall, and grows still more so up the bay. Westport, bay mouth, rise 6 hours 31 minutes, fall 5 hours 54 minutes. Wareham, R, bay head, rise 6 hours 55 minutes, fall 5 hours 30 minutes. This is anomalous, yet it is to be remembered that there is no progression between these points. The tide reaches them about the same time. Narragansett Bay is an undoubted drowned river, or rather two of them. The several channels complicate the topography. The ranges mount up from 3.1 feet and 3.6 feet at the entrance to 4.9 feet at Nyack Point. Thence it diminishes to 4.4 feet at Providence. Even here the close adjustment of co-tidals to shore contours appears in the fact of nearly simultaneous high water at Saconnet, Prudence Light, and Point Judith. The lingering rise of the tide noted in Buzzard's Bay appears here also. Bay mouth, rise 6 hours 25 minutes, fall 6 hours. Bay head, rise 7 hours 5 minutes, fall 5 hours 10 minutes. The bay head observation is at Providence, where there is some tidal progression. In this case, then, the wave has become less steep-fronted as it advances. In Vineyard Sound, again, the co-tidals are seen to be contouring ones and strongly contouring. It is difficult to comprehend how this can be a local development of a long wave front progressing across the Atlantic. Only from Gay Head to Woods Hole are there clear signs of progression. In the Bay of Fundy, high water reaches points near the head of the main bay a few minutes before reaching the main coast, just outside the bay entrance. Long Island Sound gives another surprising illustration of the same tendency. This conception of a contouring wave front seems to introduce an element of confusion. There is something very reasonable, simple, and satisfactory in the earlier idea of a long wave crest, straight or only gently curving on a long radius. Yet, even in the shallow waters that rear up considerable waves, this view is seen to be untenable. Thus, the tide reaches Sandy Hook 30 to 45 minutes earlier than points farther out to east and south, so also in St. Peter's Bay, Cape Breton Island. As already stated, this contouring tendency of the co-tidals became evident to Dr. Whewell as soon as he had good data to work on. He saw that on the Atlantic coast of North America, too, the lines must be bent along shore, though he did not draw them. Airy, in the Encyclopaedia Metropolitana, suggests that the co-tidal line is to be regarded as the crest line of a great wave, sweeping from shore to shore, as it might be seen by an eye far above the earth. The characteristic feature of such a wave is that every point of the ocean is regarded as first rising, then falling. Such was probably Whewell's conception, and it is widespread today. Yet, with the abundant data of today, it is not possible to comprehend how a progressing wave should adapt itself so completely to the shores as it is found to be the case. An advancing wave would doubtless tend to adjust itself to the shores of an estuary, but the adjustment observed is more than a tendency. Opposed to this conception is that of a stationary wave, conceived to have a medial point without vertical motion, called a node. Contemporaneous with a rise of water on one side of this node occurs a fall on the other. For the ocean there is no progression of high water, The whole water body swashes alternately east and west. For an ocean to oscillate about a node in adjustment to the moon's apparent motion is only possible with a given relation between depth and width. By counting the oscillations in 5 or 10 seconds with various depths of water in a bowl or tumbler, the reader may satisfy himself that for each combination of width and depth there is a constant period of oscillation. If the North Atlantic has such an oscillation in a period of a lunar half-day, it must have the width and depth that correspond. Growth of the later view. The first suggestion of such an oscillation was by Young. We may therefore consider the Atlantic as a detached sea about 3,500 miles long and 3 miles deep. The depth he assumes from theoretical considerations. He considers that the wave from the Southern Ocean might meet the local oscillation about Gibraltar, where it would doubtless superpose itself upon it. The moon's relation to the motion of the detached ocean is thus suggested by Dr. Young. The oscillations of the sea, constituting the tides, are subject to laws exactly similar to those of pendulums, capable of performing similar vibrations in the same time and suspended from points which are subjected to regular vibrations, of which the periods are completed in half a lunar day. Just as the hand that supports a pendulum may maintain its motion by a gentle lateral movement, so the moon's attraction may apply a periodic impulse to a body of water deep and wide enough to oscillate in half a lunar day, and thus make its oscillation perpetual. Admiral Fitzroy, in 1863, republished some suggestions of his own of earlier date that the North Atlantic tides, among others, seemed better accounted for as an oscillation as of water in a basin, or a libration as a mass of jelly, than as a progression of a southern tide wave. His argument points to irregularities in any system of co-tidals, the absence of significant tide in the Plata estuary, opening fairly to the supposed ocean tide, and the relation between times of high water on opposite shores. In the North Atlantic he found high water on the American shore fairly synchronous with low water in Europe. In 1879 Mr. Henry Mitchell pointed out that high tide is fairly synchronous from Newfoundland to Hatteras, omitting the Gulf of Maine. Moreover, along this outer coast, flood tide current sets to southwest and ebb to northwest. These two facts and the phenomena of the Gulf of Maine are more intelligible on the hypothesis of an oscillating North Atlantic than on any other. The current would result from the northeast-southwest trend of the coast, confining an ocean oscillating east and west, a portion of the westward motion being resolved parallel to the coast. The stationary wave in the North Atlantic. It has been noted above that Dr. Whewell's data of 1836 showed him that the American co-tidals were imperfect. Though he did not redraw the line, he stated that the 12-hour co-tidal should be nearer the coast, and Dr. Bache drew it closely contouring from Nantucket to Hatteras and south. It is well established now that, omitting the Gulf of Maine and other enclosed areas, the tides are fairly synchronous from Newfoundland to Florida. The Great Atlantic Oscillation belongs to the Deep Basin. Across the continental shelf, both east and west, the disturbance is transmitted as a progressive wave, and of course delayed in transmission. As a rough outline of the Atlantic Basin, I have dotted in Figure 1 the portions less than 2,000 fathoms deep, not that the continental shelf attains anything like that depth, but the descent from the shelf on east and west falls rapidly to that figure. The ocean basin is thus slightly larger than the parts left white on this sketch. The Atlantic basin is seen to approach much nearer the Spanish and African coasts than the American or the English and Scandinavian. Sable Island, east of Nova Scotia, lies close to the margin of the continental shelf and has its high water 6 hours 28 minutes after high water on the west coast of Spain, and about 2 hours before the actual American coast farther west, just as the Spanish coast has its tides earlier than the British Isles and northern Europe generally, where a true progressive wave exists and travels across the shallow waters. This oceanic basin is so shaped and proportioned as to possess an oscillation period of half a lunar day, and twice a day the moon's attraction inclines its surface now east, now west. The figures for Sable Island and Spain show that low water on the east coincides with high water on the west. As the ocean basin is not bounded by straight lines, every tongue of deep water that advances among shallows toward the land transmits the tidal impulse synchronously with the swaying of the Atlantic. In the shallows, progressive waves carry the impulse further. Whole bays respond to the oceanic movement, and only in exceptional areas can cotidals be truly drawn. The Irish Channel in Whewell's second chart and the Gulf of St. Lawrence well illustrate the limitations of the cotidal. The great coastwise ebb and flow of the Atlantic currents govern the long lines of bars and sand islands of the eastern United States. It is noteworthy that the so-called Atlantic Ridge, really a broad, gentle swell, must occupy about the same position as the node of the ocean oscillation. One is tempted to speculation on possible accumulations of finest ocean silts in this stiller axis of the swaying mass through the long ages of geologic time. One may wonder again if the moon's periodic impulse does not forbid a departure of the ocean basin from the form demanded for an oscillation in harmony with lunar time. In other words, whether the moon may not have contributed to the permanence of oceanic basins in governing oceanic tides. The tide must resist any attempt to change its period. End of section 2.